Okay, we're ready for the notes for 2G for the Math 4 course. This is supposedly funny because if something has an r-squared value of 0, that means that the line of best fit really, really stinks, as in it does not fit at all. So, yeah, he creates a linear regression line and then doesn't notice that the r-squared is 0, which means that your line means nothing. Yeah, you did not get a line of best fit. You got a line of worst fit, actually. But anyway, all right. Today we're going to talk a little bit more about residuals and residual plots. Um, and residuals are all about determining the goodness of fit, whether the line is best fit or not. So we'll start with that. Residuals, we've talked about the r-squared value. R stands for residual. All right, it's helped to determine if a curve or a shape is best fit for the data. Now, the residual singular is the difference between the observed y value, that is what your data is telling you, and then the projected or predicted y value according to the line of best fit. Line of best fit equation. All right, the residual, and as we scroll up and see these pictures here, each of those red lines in that drawing represents a residual. They represent the difference in y between the purple diamonds, which is the actual data that you're plotting, and the distance from them to the line of best fit, which is the blue line through the middle. And so each of those represents a residual, an R value, if you please. And by the time that they add them all up, they figure out whether or not your line is going to be, right now this would be considered an upward slope, a positive slope. We are going to talk about positive and negative slopes when we're talking about residuals. Of course, by the time, if you're playing with R and then you square it, negatives mean nothing, so right now we're not to the R squared, we're looking at the R. The best fitted curve is one which has the smallest sum of the squares of the residuals. That's where the squared part comes in. I'm going to take all of those little distances and square them and add them together, and that's the R value. Now, the regression line of best fit is best known as the least squares curve. By the time you start getting into statistics and such, they're going to stop calling it the line of best fit, and they're going to start calling it the least squares curve, which, again, it's just the line of best fit. All right, so this guy, the idea was to look at this chart, both linear and quadratic, and record their r-squared values. We have to write the equation as well. And so I've done a screenshot of what it would look like. So we can say that m and x, if we're going to do the linear, m is 1.1, y equals 1.15x plus 765. That is all that's needed for the linear equation. The r-squared value is 9248. Which is pretty good. If I'm going to use a line of best fit to make a prediction on something that's not in my data set, I'm going to want an R-squared value of at least 0.8 or 0.9 before I feel comfortable with the kind of prediction that it's going to make. Otherwise, you talk about, what is it, margin of error? Oh, we're going to get into that in statistics too. But anyway, all right, so that is the linear taken care of. Now the quadratic is negative 0.125. And then B is 2.4. So we'll say plus 2.4x. And then the C value is 5.525 plus 5.525. And then we say that the R-squared value is 986. I've about come to the conclusion that unless your dots are exactly in a straight line, there's always going to be a quadratic that's a better fit, because the quadratic has the ability to bend to fit the needs of the data. All right, so that is example 2. Now for example 3, I have to confess I made an error when I set this up, that these should be R values, not R squared. When you think about it, R squared cannot be negative. R squared would have to be positive. But the idea is this, that as you are looking at a set of scatter dots like this, the question becomes, how close are they to that line? Are they clumped up together like this, or are they spread out like a cloud, like this guy over here? And so, when your R value is close to 1 and everybody's close to that line, I would actually use the terms strong positive correlation. When I get to this guy, it's still positive because the slope is still going uphill. This one's going downhill, so it's negative slope. But this one is still a positive slope. And it's close to 0, so there's not a whole lot of correlation going on. But if I had to choose, I would call it a weak positive correlation, and that it's closer to 0 than it is to 1. It's going to be a weak. There is a correlation. They were able to come up with a line of best fit, but there is so much, so many of these points are still a good ways away from that line. All right, here, negative 75. 0.5, negative 0.5 would be closer to 0 than negative 1, and this guy is actually a little closer to negative 1. So I think we could still call it a strong negative correlation. About the time you start getting close to negative 0.5 and getting close to 0, then you start, doing the weak side of it. And so you're going to have some of like that over for homework, and also you're going to have probably at least one question on the test that'll show you a scatter plot like this and ask you, is this strong positive, weak negative, or strong negative? Okay. All right, one last one here. I think we got two last ones that are basically doing the same thing. When I graphed it, I had a graph that looked like that. And once again, even though my linear was pretty close, my quadratic could get even closer. So this is what we're going to write for our equations. 2.16. 2.16. And negative 14.73 minus 14.73. R squared value is 9931. And when we look at the other one, we have our A and our B and our C. That's 0.3. Y equals 0.03 x squared. And then B is 0.917. We'll call that 0.92. 0.92x comes next. And then the last term, negative 4.41 minus 4.41. And my residual there is 998 for the quadratic. Okay, so that's what 4 should look like. And again, you are comparing the R squared values to see which one is the better fit. Okay, number 5, we give this table. And by the time we graph it, our dots are looking like that, which we've seen some better fits. As a matter of fact, you look at the R squared values and you realize that this is not quite as strong as they have been because you've got more distance between the dots and their lines. So let's start crunching some numbers here. You have negative 0.94 to start off your linear. Negative 0.94. Come on. Oh, I got it backwards. Negative 0.94x and 23.52. And our R squared is 6075, which I still would call it a strong correlation. It's closer to 1 than it is to 0. All right, quadratic A is negative 0.11. X squared. Next term is 965, which would be 97, plus 0.97x. And then the C value is 1793. 6 would be 1794. And the R squared value down there is 7261. All right. There wasn't a whole lot of new meat to this other than, discovering about the R values and the strong and weak correlations, positive and negative correlations. That was one of the larger issues here. And also just getting used to the idea of comparing the R squareds as to which equation is going to turn out to be a better fit for making predictions off of this data set.